All right, so next week we'll have another lab, the second lab. And I'll send out the email about this. Also, I'll put this information on Moodle. So next week we'll do the same thing as we did last time, like 2 weeks before. I'll send also the instructions, like procedures. So please read it ahead. So be prepared for the lab. Otherwise, it will be the same thing as it was like in the first lab, because I mean, people, we are not prepared at all. So I'll send out these instructions and procedures. So please keep eye on the email. Also check the Moodle frequently. Any questions about the lab?
Doctor, how much we have left?
There's 5 points. Both labs are 5 points. The first lab is 5 points, and also the second lab is 5 points.
And just 2 left.
Yeah, just 2 labs. This is like as according the syllabus. It's just 2 labs. Okay. All right. So
Doctor,
yeah,
Doctor, the presentation, how much mark?
10.
10 mark.
Okay, could you please download the syllabus? So in syllabus, everything says what is how much. So just download the syllabus and please read the syllabus, and it says like every detail about what is presentation, how many marks, and everything. Yeah, it's 10 points. Okay, any other questions? All right, then I just continue the class. Okay, so today we'll talk about, so basically we finished inorganic chemistry, let's say, or general chemistry. So now we'll go to the organic chemistry. And from now, mostly we'll be talking about organic chemistry. It will be quite important for you to prepare for biochemistry, because next semester you will take biochemistry, and it will be really helpful to go through organic chemistry, so you'll be kind of okay with biochemistry. All right, so before we go itself organic chemistry, I want you to remind you about the bonds which are in between atoms in different molecules, right? And in organic chemistry, we'll mostly have covalent bonds, covalent bondings, and so the covalent bonds is the strongest bond actually among all bonds which we know. So during these bonds, what is happening that the shared electrons are equally shared between 2 atoms. And it's not like shifted, these shared electrons are not shifted to any of the atom. Okay, and this is quite considered as a strong bond. For example, in water we have covalent bonds. This is hydrogen plus oxygen. It creates water. In water we have covalent bonds, and it's bound covalently. So hydrogen and oxygen are bound to each other covalently. So how the bond is formed in general. So there are 2 forces which makes the bonds to be formed. So if you look at this scheme over here, so say this is the atom, right? And this is the nucleus in the middle, right? The nucleus is charged positively, okay? And so this is positively charged nucleus, and around nucleus there is a cloud of electron which is negatively charged, right? And so what forces build the bonding between atoms? So one is repulsive forces, which are between nucleus, okay, between these two nuclei, because both of them are positively charged. So this is repulsive forces. And the other one is also repulsive forces between cloud of the electron, right? So we have electron here, and they repulse also each other because they have the same charge. But there is also attractive forces which are between nuclei. So look at this blue line. So between nuclei and cloud of electrons. So these are attractive forces. And this is basically what determines the bonding in the molecule between atoms, okay? So if we try to show the bonding using Lewis structure. So this is Lewis dot structure, so-called Lewis dot structure, when electrons are depicted as dots. Okay, so for example, if this is water molecule and we have shared electrons between hydrogen and oxygen, right? And we can also express it as this line. So this line means that there are two electrons shared between oxygen, hydrogen and oxygen, okay? Or for example, in carbon dioxide, so there's one electron from oxygen, one electron coming from carbon, and also one electron coming from another oxygen. So eventually the bonding is built up like this way. So these are shared electrons which are created from this electron, and this another pair is just coming from this one and this one, okay? So overall, we have two pairs of shared electrons between carbon and oxygen, and between another oxygen and carbon. The same thing, these electrons are shared, and also these electrons are shared, okay? And eventually, we have double bonds between carbon and oxygen. Also, there might be triple bonds, for example. That's also possible to make triple bonds. And this is how the Lewis structures are expressed using either sticks, either dots. Depending on whether there is single bond or double bond between atoms, the size of the bond differs. For example, for single bond, if we compare, let's say, compare these three cases, because all these bonds are between carbon-carbon, carbon-carbon, and carbon-carbon, right? But you can see that this is single bond here. This is the single bond, and the length of this bond is 154 picometers. Okay. So this picometers is basically 0.154 angstroms. Okay. So picometers is 10 to minus 12 meters. So, but if you look at the double bonds between carbon-carbon, you can see that there are that the bond size, the bond length is 133. All right. So it gets smaller, right? As the number of bonds increase, it gets smaller. It's logical because it's tightly binds now. Two carbons bind each other tightly because it depends now on double bonds, right, rather than on single bonds. So, and if you take like triple bonds between carbon-carbon, it's even smaller. So it's 120 picoamps. And the same thing, if you take like carbon-nitrogen bonds, you will see the same kind of trend, right? And this is normal because there is a increase of number of bonds. So usually this length is taken as from the center of one atom and the other atom. So basically this is the length of these bonds, bonds created between atoms. Well, now this is about just because
Dr. we must memorize the length between bonds.
No. There's no need to memorize this kind of numbers. Just to know that the bond length decreases as bond number increases. Just to understand that this just gets smaller and it gets stronger. These bonds are getting stronger. Okay, so now let's just go to the introduction to organic chemistry, well, the main element in organic chemistry, basically, we can say that it's carbon. Carbon is very unique element. It's over here, so it's very unique, and this is basically what creates the backbone, basically, of organic molecules. It started in 17th, like 18th century, when the compounds we obtained from living organisms, living sources, and it was found that they differ from minerals because they are soft. You know, it's very often it was liquid. Very quickly it could melt. So it was quite different from like mineral or compounds. Then you know, also it was difficult to purify these kind of compounds, and so it was obvious that the compounds from living organisms were different from, say, just taken from earth, for example. So just to make this difference, those compounds were called organic compounds. So, and then this was the starting basically of development of organic chemistry. But it's not, of course, only those compounds which are taken from living organisms. Also, there are so many synthetic molecules which belongs to organic chemistry. And the variety of these molecules really huge, because you might find very small molecule, say methane, CH4, which is very small molecule, but also some molecules are just huge. For example, some proteins, some DNA, for example, it's a huge molecule. Basically, the organic chemistry is defined as a discipline which studies carbon-based chemistry. Again, so the chemistry which deals with carbon compounds is organic chemistry, and you can see that it's a big variety. You can find organic chemistry everywhere, and one of the also important part of organic chemistry is functional groups. Like it says here, functional groups, which is the group of atoms which basically determines the chemical behavior of the parent molecule. For example, if you look at this molecule, which is capsaicin, and this the burning sensation of chili peppers such as habaneros, this is Mexican chili pepper, very, very spicy and hot one, is mostly due to the organic compound called capsaicin. Okay, so you can see this capsaicin has different functional groups. For example, this is carbonyl group, this is functional group, this is amine group, this is also functional group, this is hydroxyl group, this is also functional group. Okay, all these are, for example, double bonds are also considered as functional group. So these functional groups determines the kind of properties of organic compounds. Yeah, so the base of these organic molecules is the hydrocarbons. All organic molecules are then derived from a group of compounds known as hydrocarbons because they are made of only hydrogen and carbon. We can divide these hydrocarbons in two main classes, aliphatic and aromatic. So aliphatic hydrocarbons do not contain benzene ring. So this is benzene ring, for example. And aliphatic hydrocarbons do not contain benzene ring. But aromatic hydrocarbons, for example, this hydrocarbon you can consider as aromatic because it contains aromatic hydrocarbon ring. We will talk about each of these classes because it's quite important. What is very important to remember is that carbon is tetravalent. So what does it mean is that I showed in the previous slide. So carbon has 4 valence electrons. Okay, it has 4 valence electrons. It can create 4 bonds, and we need to remember that it creates 4 bonds in organic compounds, not 3, not 1, not 5, but 4 bonds. So if you look at this scheme, basically it just differentiates aliphatic and aromatic hydrocarbons. Aliphatic hydrocarbons can be also divided by alkanes, cycloalkanes, alkenes, and alkynes. Okay, we'll go through all these compounds. Again, carbon is tetravalent and it always forms 4 bonds. You need to remember this very well. So the carbon always forms 4 bonds in organic chemistry. For example, if you take methane, so this is the methane, CH4. Sorry. So this is the gas which we use to cook. For example, at home we burn this gas to have some. So basically, this is this one. Okay. So you can see that this carbon in the center forms 4 bonds with hydrogen, right? 1, 2, 3, 4. In space, in 3 dimensions, you can say that this is tetrahedral. So this is the arrangement of hydrogen atoms around the carbon. As I said, organic molecules have covalent bonds. In methane or in ethane, the bonds result from the sharing of 2 electrons, either between carbon-carbon, either between carbon and hydrogen. For example, in methane, it's only sharing between carbon and hydrogen because there is no other carbon, right? But if we take ethane, this is ethane. You can see here that this 1 bond is shared between carbon-carbon, and other bonds are between carbon and hydrogen, right? So, so sometimes for example, hydrogen can be substituted with other element, as it is in this particular case with chlorine, for example, and these covalent bonds become a little bit shifted towards the electronegative element, which is in this particular case, it's chlorine, and a little bit the bonding becomes shifted, okay? And because of that, the whole molecule becomes charged from one side and from the other side. So basically it becomes a little bit dipole. So you can see this is potential map, and it shows different colors for different atoms, okay? This is called polar covalent bonds, like when there is a little bit shifting of the bond. So carbon can form multiple covalent bonds. For example, it can form double bonds, it can form single bonds, or it even can make like triple bonds, okay? So all these are characteristic to carbon. It can make all these type of bonds. For example, we'll come to that point just to say that if it forms 2 bonds, it was ethane in the previous case when it was single bond, but now it can become ethylene because the name also changes depending on number of bonds. We'll go to that point as well. Yeah, so organic molecules, well, not only like just carbon and hydrogen, but also it might have other atoms as well. For example, it can contain nitrogen, it can contain oxygen, right? And also they can form like single bonds. For example, we can have carbon nitrogen single bond, or carbon nitrogen double bond, or carbon nitrogen triple bond, because what is happening that nitrogen has 3 unpaired electrons. It's like this one. And carbon is like this. So all these 3 electrons can be shared, right? All these 3 ones. And then there is one more electron which can be shared with another one.
With hydrogen.
Yeah, for example, with hydrogen. Yeah, right. So, so this can happen with organic molecules. This is just we will not go deep to hybridization, but usually this is about atomic orbitals of organic molecules, and they are hybridized because initial shape of orbitals, we will not be talking about this one too much. Initial shape of orbitals are, for example, sphere or this dumbbell shape, but then when they mix with each other, they are hybridized and they make different shape in order to arrange the molecule in a particular shape. We have sp3 hybridization, sp2, and sp hybridization, okay? So covalent bonding makes organic compounds quite different from the inorganic compounds. So this is basically one of the reasons that they have particular characters, these organic molecules, because of these covalent bonds. So another difference between organic molecules and inorganic compounds, it's about solubility. So when the organic molecule is quite big, it's not really soluble in water. And you know that you have maybe seen that there is, for example, contamination of sea waters from the oil, because oil is quite a big molecule, big organic molecule, and it doesn't dissolve in water. And you can see some contamination coming from this oil, right? So this is a basically problem if something like that happens. So it's practical, actually, practical importance of the feature which is related to solubility of organic molecules. It's basically the lack of solubility. For example, because of that, one thing is that, again, as I said, it's very difficult to clean up spill from oil compounds, oil and its derivatives. But in another hand, it's important to have this kind of thing not to be soluble in water. So for some practical purposes as well. But it doesn't mean that none of these organic molecules cannot dissolve. Some of them dissolve, but big molecules, as I said, big hydrocarbons do not dissolve in water. For example, you have seen if you mix oil, just not gasoline, I'm talking about just food oil, right? So which we use at home. They never miscible oil and water, right? Yeah, so by the way, cells use membranes composed on water-insoluble organic molecules. It's also very important that it's water-insoluble organic molecules to enclose their watery interiors and to regulate the flow of substances across the cell boundary. It's very important to have this character to be soluble or not to be soluble. Yeah, so the functional groups, let's just mention about functional groups. These are very important part of organic molecules because they really change the properties of organic molecules. There are so many organic molecules, like 18 million organic compounds are described in the scientific literature. It's not like new data. So there are some more every day. People are synthesizing some new organic molecules. So there are very, very many organic molecules, and they differ from each other, like having different functional groups, for example. So the structural features that allow us to classify organic compounds into distinct chemical families are called functional groups. So the functional group is an atom or group of atoms that has a characteristic physical and chemical behavior. So which gives organic molecules some specific properties. Yeah, by the way, what is very interesting that wherever these functional groups are located in whichever molecule, doesn't matter. So they have the same property and they undergo the same type of reaction. It doesn't matter on in which molecules they are. Yeah, by the way, this chemistry of organic molecules very much is determined by functional group, and it's not because of size or complexity. It's because of the functional group. For example, if you look at this small molecule, which is ethylene, and it has double bonds over here, this one can be considered as functional group. Okay, this double bond is a functional group. And if we add like hydrogen, we just make ethane. And so what does it mean? That it's possible to add hydrogen to the place where we have double bonds, even though the molecule is small, so we can add this hydrogen, we can make ethane. And these double bonds is really for that. So, but if you take big molecule, and you still have these double bonds in there, so you can add hydrogen, and again, you can do so. All right, so it doesn't matter like how big is that. If you have these double bonds in there, you can add hydrogen to the molecule. These are just structure and the compound names of different organic molecules, and we'll be studying some of them, basically all of them. So we'll be studying alkenes, alkynes, alcohols, ethers, aldehydes, ketones, carboxylic acid, ester, amines, okay, amides. So we'll be studying all of this, and you can see the structural differences between them. So alkene has double bonds, alkyne has triple bonds, alcohol has this kind of OH group, ether when oxygen is between two carbon groups, okay, and so on. We'll go through this one step by step. So this is the formula here, this is the name, and this is some kind of three-dimensional structure. Okay, now let's just go with the simplest one of organic compounds, and that one is alkane. Let's start with alkane. So hydrocarbons that contain only single bonds belong to the family of organic molecules called alkanes. So again, so there should be only single bonds. Say if you have double bonds, it's not alkane anymore. So there should be only single bonds in there, and that one can be considered as alkane. For example, the simplest molecule of alkane is methane. That's the chemical formula. Okay, this is the structure, like structural kind of depiction of methane. Okay, so this is the simplest one, but for example, we can have also different molecule of alkanes, which can be, for example, ethane. In ethane, you can see here, you can take 2 carbons and add 6 hydrogens, and then you can make alkane, which is called ethane. So the general formula, say, if we describe number of carbons as n, okay, so if it is number of carbons, then we can say that general formula for alkanes is CnH2n plus 2. All right, so this is the general formula of alkanes. So if I take, for example, C4, what's going to be the number of H?
10.
Of course,
10.
it's going to be 10. Yeah, it's going to be 10, and so on. I mean, you take whatever n of carbon, you will get the number of hydrogens, and we should remember that there is only single bond between carbon and hydrogen.
It's called sigma, right?
Yes, it's sigma bonds. Yes, it's sigma bonds. Because you can think why it's sigma bonds, because we as I said, the orbitals of carbon are hybridized, and eventually they create, for example, for CH4. So they are hybridized and they create this kind of shape. Okay, because there is two orbitals combined, s orbital and p orbital, and the hydrogen comes to this orbital like head to head. Okay, and this kind of head to head bonding is considered as sigma bonding.
Doctor,
Yeah.
we must know the name of like methane, ketane.
Yes. So you must remember. I'll tell you. You must remember first 10 alkanes. First 10. It's not difficult actually, by the way. All right, so let's just continue with alkanes, what they can do. They can make isomers. So what does it mean it's isomers? So the formula is the same, but the structure is different. For example, if you look at these two pictures here, so both of them are C4H10, butane. Okay, so if we combine 4 carbons with 10 hydrogens, we'll make butane. But they can make it like either in a straight chain, like this one here. So all these carbons are in a chain, right? Or they can make it a branched one. For example, like this one. So, right? So we have 3 carbons in a chain, but one is like attached to the middle one. The formula is the same for both of these two. Both of them are C4H10. But again, the structure is different. If you look at the 3-dimensional structure, this is how the straight chain looks like, and this is how the branched one looks like. So these are isomers. They are called structural isomers. Of course, there are some constitutional isomers as well. We'll not be like discussing too much about that, but you should know that, for example, you might have the same formula. This is ethyl alcohol and this is dimethyl ether. But depending on how atoms are arranged in this molecule, they are completely different compounds. They are not really the same compound. For example, in the previous case, these two are the same compounds. Both of them are butane, both of them are alkanes. So they belong alkanes, but in here, in this case, one is alcohol and the other one is ether. Okay, so because you see this oxygen is in between carbon and hydrogen, and here it's between carbon and carbon. So this is ether and this is alcohol. Okay. For example, alcohol is central nervous system depressant, or ether is anesthetic. At high concentration is anesthetic. It was used in the past as anesthetic. Now, how to draw the structure of organic molecules? So there are different type of drawing. So one is structural formula, for example, this one. Okay, and you can see that it just use these sticks to represent bonding between carbon and hydrogen. Another case is when it's condensed formula. Okay, so there is no sticks over here. See, this is just a chain of this CH3, CH2, CH2, CH3. So it can be represented also this way as well. The same thing about the branched one. So the branched one structural formula is this, and the condensed formula is this one. So here, of course, this branching needs to be indicated. So here we need to use this stick. Also, you might have a line structure representing also organic molecule using like so-called line structure. Okay, so what does it mean, this line structure? So look at this one, please. There are some lines, right? But what does it represent is that it implies that here is CH3. Here we have CH2. Okay, here we have CH3. Here we have CH2. And here we have CH3. Okay, so but you can just you might not write it and using this line structure, just only like, you know, this one over here. So what's going to be this one? How do you think? Can you tell me that? Yeah,
in the first.
so can you tell me the formula for this one?
CH3, CH2, CH2, CH3.
Right, it's going to be CH3, then it's going to be CH2, CH2, CH3. Right?
But doctor, in the first example, there are one CH. Where we must put it? Yes.
Where? Here?
Yes.
Well, oh, I'm sorry. Yeah, you're right. So okay. So this should be only one CH. This is what you're saying? Yeah, exactly. So this was wrong. I'm sorry. Yeah, thanks for that. So it's only one CH because, so why did it's only one CH? Because we have one bond with this, the other bond with this one, the third bond with this one, and the fourth bond with this hydrogen over here. So we can have only 4 bonds for carbon. Okay, do you guys have questions about these line structures and stuff like this?
No, doctor.
Okay. Now let's just see the shape of organic molecules. Again, you know, they can change the shape, especially alkanes, because they're free to move in some parts. For example, if you take this butane, so there's the butane, and it has some kind of one structure, but also it can have this kind of structure, right? So it's called conformation. And it's quite important because, for example, proteins also undergo conformation. So they are free to rotate, say, in this part, because they have only single bonds here. So it's not that difficult to rotate the parts of this molecule and then like change the structure of the molecule. Okay, so now it's about naming of alkanes, and I have only just 1 minute left, a little bit more than 1 minute, and let me see if we can. Okay, so maybe we should we should do it maybe next class. I can just stop here maybe, and I'll upload this PPT file, and next time we'll come and finish this part. But you know what? Let's just finish here. I just need 10 minutes more to finish naming of alkanes. At least let's finish with naming. Okay, I have less than 1 minute, but please come back after that. Okay, so well, to name the alkane, so first of all, we need to understand that there is some particular agency which basically establishes the official names of compounds, and it's called Union of Pure and Applied Chemistry, UPAC. And we must know, like, you know, that the name is according to this UPAC. And there are 3 parts in the name: prefix, parent, and suffix. Okay, so we have prefix, parent, and suffix. So let's just start with parent. So it shows how many carbons we have there. That's the parent. Okay, the prefix, it shows us where the substitutions are located.